Yeah, okay. Good evening, everyone. Welcome to week 7 problem solving session of computational complexity. Again, my name is Bhavya Rai. I'm a research scholar at IITM. So, let's the topic for this week is actually uh, a bit of randomized complexity, but we did a lot of that in last time's session. So this time we'll be focusing mostly on the next part of this, that is in fact week 7 is completely consisting of circuits, right? So this time it's only circuit complexity. So uh, and I'll give a recap on what circuits are and so on, because last week's session, week 6, was also based on circuits, as the final part of last week's session was based on circuits, and and a few questions on the assignments were also based on circuits, and we'll look into solving them, and then we'll solve a few questions on circuits again, and I'll do a bit of recap. Okay. And yeah, this will be a shorter session compared to previous sessions, probably. Okay. So circuit complexity. Um, we know what circuits are, but to recap, I'll come back to I'll show it again. A circuit is a DAG, a directed acyclic graph. That means a cycle cannot happen, but it's a directed graph. There's a certain direction here, and it has n input bits. So we are talking about a Boolean circuit. Okay, there could be other types of circuits, but we are talking about bits, n input bits, and vertices are gates. For example, and or not. You could have other types of gates also. Let's say XOR and so on. That could be the case. Now, and then finally, um, um, vertices are gates and edges are called wires. Okay. So it's like a circuit you would build physically. It's like the hardware. Okay. And which is composed of AND gate or gate and so on. And you may have seen in your undergraduate courses that we can build, adders, comparators, multiplexers, decoders, and all sorts of interesting things. And so circuit is therefore a computational model. So, and circuit is a computational model. And but what is a formula? Okay, what is a formula? A formula is a formula can be something like, an example is something like x and y bar and z, or x bar and y, and so on. This is a formula, right? So in other words, okay, formula is just circuits that are trees. Okay. I forgot to give you an example of circuits. A circuit looks something like, or, and then and then x1, x2, x3, x2 bar, let's say, and here another and, here is an OR gate, and here is x, here is x4, and here let's say it takes this input, and and let's say this AND gate takes two inputs, three inputs. So it takes the input from here also, and the directions are upwards. Right? This is an example of a circuit, and it computes some function. And one thing you can see is that this particular node and this particular node, okay, both of them have out degree 2, whereas all the others, for example this node, this node, this node, all of them have out degree 1. Now out degree is also called the fan out of the gate. Okay. Out degree is also called the fan out of the gate. Now let's say I do not allow this. I do not allow fan out to be more than 2. More than 1. Then
So what is the meaning of having the value of the fan out is equal to 2?
right, fan out 2 simply means that I am able to copy a computation. So if I have a gate, okay, let's say I'm doing a fan out 2, okay, then it is possible to have a gate which feeds into two other gates. The output of the gate feeds into two other gates. Okay, this is the first one which feeds into some other gate. Let's say it feeds into an OR gate. Okay, let's say it feeds as an input to an OR gate, and this feeds into another OR gate, something like this. Let's say this is an AND gate. So this guy has a fan out of 2, right? It is feeding into two different people. Getting it?
Yes.
So what you are essentially doing is you are simulating a copy operation. You're simulating a copy operation in a sense that instead of taking the pain of computing this part of the circuit twice, you actually took two wires and then plugged them into two different points.
Yes.
Right? But formulas, okay, formula is fan out strictly equal to 1. That is, out degree is equal to 1. So what do you call such structures, such DAGs whose out degree is at most 1? It is exactly what you call trees. What you call as trees.
So what is the difference in between a DAG and a tree?
Yeah. So I'll give you an example. See, a tree is a DAG, but a DAG is not always a tree. Okay. Why? I'll show you. What does a DAG mean? No cycles. Okay. We are talking about directed graphs. Okay. So a directed trees and directed acyclic graph. Okay. A DAG has no cycles. If you talk about undirected setting, DAGs are or acyclic graphs are same as trees. Okay, but we are talking about directed graphs here. A DAG has no cycles. Okay, and a tree, okay, has degree at most 1 for each vertex. Okay, now here is an example. I'm going to ask you um, so is this a DAG?
No, this is not a DAG.
Okay.
This was the cycle.
Yeah, where's the cycle?
cycle is from A to B and then B to C and then from C to A.
This is not a DAG, right? Correct. That is the cycle. Now, I'm going to ask you, is this a tree?
No, this is not a tree. I mean, this is not a tree.
Right.
Not a tree because from in a tree, from a node to any other node, we do have a unique path.
You have a unique path. That is correct. Okay. Now let's see another example. Yeah. So this is another example. Is this a DAG?
Uh, yes, this is a DAG because I mean, it does not form a cycle. However, this is not a tree.
But this is not a tree. You can see, right? This is not a tree. Because here what you have is the in degree is greater than 1. Or in other words, in your definition also, it is not true that for every vertex there is a unique path between them.
Yes, and why the in degree is more than 1 here? Because in degree of all the vertices, yes, for the vertex D, the in degree is more than 1.
Right.
Yes, I understood.
Okay. So, but in the case of circuits, we are talking about out degree because our vertices are pointed upwards. Okay. So we can equivalently say that out degree cannot be more than 1. Okay, for formula, sorry, not in the case of circuits. For formulas, we say that the out degree cannot be more than 1. Okay, because our outputs are feeding upwards. Anyway, this is a DAG, but this is not a tree. Yeah.
Can you repeat this conclusion about the degrees for the tree and then for the DAG?
Yeah. So, for a formula, okay, this is allowed because this is a gate, right? So a gate can have 2 inputs. So in degree can be equal to 1. But this is not allowed. Equal to 2. This is not allowed. The out degree is 2 here. Because the gate is, the copy operation is what we want to stop.
Yes.
Okay. So this is the tree. This is a DAG, not a tree. Similarly, you can say something like, this is not a circuit. And this you can say it is not a formula, equivalently. And you can say this is a circuit, this is a valid circuit. And here you can say not a formula. Okay. So a formula, if you make it, okay, if you make it into a diagrammatic representation, it will always look like a tree. For example, you can, any Boolean expression is always a formula. Example, if I write x1 bar and x2 bar and x3 or x4 and x3 bar or x3 not x3 bar, x4 or x3, let's say this is my Boolean formula. I can, it is, if I can write it as a Boolean formula, that same Boolean formula exactly I can translate it into I can translate it into a tree like representation. So if you give me a formula in such a way, if you give me a representation in such a way, it's always a formula. Why? Because these three I can write it as x1 bar and x2 bar and x3 or x4, okay, and or of x3 bar, x4 bar, x4, x3. Getting it?
Yes, and this gives me an insight because I read somewhere that every algorithm can be encoded as a Boolean formula.
Yeah, every algorithm can be encoded as a Boolean formula. I mean, yeah, by Cook-Levin.
Yes. So,
Right.
and this technology also supporting this fact. Why so? Because if this circuitry, or if these circuits
Mm-hmm.
is an alternative model of the computation, say different from the Turing machine model,
Mm-hmm.
then I guess that everything which can be realized by the Turing machine can also be realized through the circuitry here. So
Definitely.
if
Yeah.
so if both the models are equivalent, so then it supports this statement that every algorithm can be encoded as a Boolean format.
That's right. That's right. Yeah. And yeah, exactly. And in fact, although it is a misuse of language to say this, I mean, but circuits are arguably more powerful than algorithms in than Turing machines in some sense because it's a non-uniform computational model. Although what I'm saying is violating the Church Turing thesis, so I don't mean literally more powerful, but um, they are capable of solving, suppose, say, undecidable problems.
Yes, and because you use the term non-uniform here, so I do not understand the difference between the uniform one and the non-uniform one.
Sure, sure. I'm coming to that. Okay.
Okay.
Yeah. Now, so and let's say, yeah. So, and what is fan-in? Fan-in is the number of inputs to a gate. So here it's three. For this gate, the fan-in is two of the gate, right? So fan-in of circuit is the maximum fan-in of any gate G.
But you have not shown the directions of the edges here. Is this okay, or do we need to show
Yeah,
that?
it is. So if the directions, yeah, one thing about circuit complexity is that if I make a diagram, then it is understood that it's bottom up. The
Okay.
directions of the arrows are bottom up. We don't write the direction of the arrows. Okay.
Yes.
Yeah. Okay. Good. Okay. So that is one thing. Now, okay, now there are already so many questions. Okay, how powerful is circuits? How much power does circuits have over Turing machines, and how much power is Turing machines more powerful than circuits? And these kind of questions. And another way of doing it is we add some kind of restrictions. Are formula as powerful as circuits? Are circuits as powerful as formulas? And for example, in the Turing machine world, what we did was we restricted the amount of space and said that okay, this log space only I give you, then it computes languages in L. If I give I allow you to run for polynomial time, then it computes the class P and so on. Right? Those are the kind of restrictions I do to obtain different to categorize problems into different classes. Similarly, we do the same in circuit complexity also. And what we do is we add restrictions into the structure of the circuit or the function computed by the circuit, and whether it's a formula or a different kind of restriction, fan in, fan out, and so on. Okay, and one such restriction is fan in. So if say formula. Okay, okay, but yeah, I'll come to this now. Before I come to this, now I'll talk about the uniformity argument. Okay, okay. So here's the idea. Okay, so I'll give you a question. Okay, that is um given inputs. Okay, x1, x2, and so on till xn. Okay, and they are all bits. These are all bits, and my output should be yes if at least one xi equals 1, no otherwise. Okay, this is the thing. Now Um, what design an algorithm for it? How does the Turing machine work?
So Turing machine will keep on moving towards right by replacing the symbol by itself until the Turing machine finds a one. And so if the length of the input is n, then at the most Turing machine may need to make n number of the right moves.
Exactly. Good. Yeah. So let's say M moves from left to right on input tape. If M sees 1, then output yes. So this is a simple algorithm to do this. Right. Now let's say, and time taken, like you said, is around order n. Now, the question I ask is, what if n equals, say, 20? Okay. If n is equal to 20, then m runs for, some c times 20 seconds. And if n is equal to 25, then m runs for c times some 25 seconds, and so on. But the key thing to notice is that m adjusts the the process accordingly to the inputs, according to what the input length is. Okay, so I'm not going to say anything further than this. I'm going to move on. Okay, and you'll understand what I'm now trying to say. That same question. Okay, same question. That is this. Okay, same question. That is this. Now I say design a circuit, a Boolean circuit, to compute this. That is, check if at least one of these bits are 1. So how do you make a circuit for this?
So I will give x1 to xn as an input to an OR gate, and if the value comes out to be 1, then definitely one of the bit must have been a 1.
Exactly. So the Boolean circuit will look like this: x1, x2, and so on till xn. Right? Now,
Yeah.
right. So your Boolean circuit will look like this: x1, x2 till xn, or not and sorry, or will look like this. Now let's say n is equal to 20. So what will your circuit look like? x1, x2, and so on till x20.
The
But what
value
if
of
n is, yeah?
fan in is 20 here. If fan in is one of the parameters, then the value of the fan in is 20.
Then the value of the, yeah, fan will become 20. That is right.
Yes.
And let's say n is 25. Then x1, x2, and so on till x25. Yeah, again, fan in will become 25. Furthermore, the size of this input will increase. And due to obvious reasons, and the fan in will change. And these two circuits are definitely not the same. Right?
Yes.
The descriptions are totally different. And this is a simple example, but there are examples where, for a particular length, okay, you have a circuit, and for another length, the other circuit looks completely different. That may very well happen.
Yes, but yes, that's true. But then these two circuits are similar, except the number of the inputs. I do not observe any other difference here. There could be more number of the wires used, and
Exactly. But similar, being similar is not enough. the circuit actually is different, okay, because the descriptions are completely different. And secondly, that's what I'm saying, that it may so happen that you may come up with an example where, for a certain length of input, okay, for let's say an odd length input, you have a certain circuit, and for an even length input, you have another circuit
Yes. Yes.
for it. It may so happen that way, and that is still valid, right? But what you understand is, for a single, okay, for now, but this problem was not there in Turing machines. No matter what the length, it will handle it. Now, so input, okay, so what is the observation for Turing, for all n, okay, lengths, input lengths, for all input lengths n is equal to, sorry, what am I saying? Okay, for all input lengths n, okay, same Turing machine can compute L, that language. And here, for each input length n, need a different circuit to compute L. Okay. For each input, you'll need a different circuit to compute L.
Yes. Yes.
Right. Now, this is what is called a uniform model, and this is what is called a non-uniform model of computation. Okay. Uniform models are like Turing machines, RAM machines, and so on. That the same description will work for every possible input length. But if the as input lengths varies, we need different models. Then that is called a non-uniform model. And a non-uniform model, circuits are not the only one. I mean, formulas is another example, but there are several other, like branching programs, straight line programs, decision trees, and it's all over the place. Okay, it's not a very rare thing.
So, what are the guidelines or what are the rules to call a model as a as a universal model of the computation? So, like if Turing is one of the universal model of the computation, then like say I have heard the names like the circuit is the one, and then cellular automata is also considered to be the other one. So, I mean, what are the rules that a model is viewed as a universal model of the computation?
Well, to um, to sum it up, a universal model of computation should be able to do whatever a Turing machine can.
Okay.
And right, so it should not, yeah, so according to uh, 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 the Church Turing thesis, any physically realizable computation that you can do on this universe can be done by a Turing machine.
Yes. Yes. Yes.
Now, any computation you can do can be done by a Turing machine. So let's go the other way around. That, can you come up with a model that can do anything that a Turing machine can? If it is so that it can do anything a Turing machine can, then it should be able to do any computation possible. So that is one thing. So circuits as a universal model of computation is because, for every Turing machine there is a corresponding circuit.
Okay.
Okay. So now, yeah, exactly that. Now I was, like, for example, so um, circuits are as powerful as Turing machine in the following sense, that I have a Turing machine M. Okay, this is a Turing machine M. I use Cook-Levin reduction. and get a circuit C. Okay. Now remember what the Cook-Levin reduction was like. The Cook-Levin reduction also depend on what the input was, X, right?
Yes.
The what the input specifically what the input length was. So you get a circuit C which depended on the length of X. So if you took another Y as the input to Turing machine M, and then you apply Cook-Levin reduction, you get another circuit C which looks very different from the circuit for X. This is not
Yes.
same, but this is same. The descriptions are same.
Yes.
Okay, so this is why it's this is why this is the difference between Turing machines and circuits basically. But of course, they can do what each other can. Okay, and at least circuits can do what Turing machines can. Now, let's take some observations. Okay, that is, so remember Cook-Levin. You have a Turing machine M, and on an input X. Okay, and then you do Cook-Levin, and you get C. Oh, okay, okay. I forgot to mention this. Okay, so before I come to this, making a lot of mistakes today. So before I come to this, so you always say this term. Okay, you don't say L is computable by a circuit C. This is wrong. Unless L consists of only single length strings.
Why so that L is computable by a circuit C is not correct? What is
This
the
is
point?
not right because if L has uh, one input of length 10 and one input of length 15, it will require two different circuits for it. It cannot be that it can be computed by a single circuit. See,
Can we say that L is computable by a set of the circuits?
exactly. So that's where we say, okay, this is a no go. That's why we say L is computable by a circuit family C, and then we put an N here, okay, to denote that this is the circuit with N inputs. C N is greater than or equal to 1 or 0 if the input is empty. Getting it? So this is what we do, because there may be several circuits which will compute the same language but for different inputs, right? So
And
this,
this N
yeah,
here is, what is N here is?
N is the
Is
input to this number of inputs to the circuit.
number.
Yeah. Here N is not number of inputs, sorry, the number of inputs to the circuit, which is input length for the Turing machine. Getting it?
Is
It is the input length. Okay. It is the input length. When we talk about Turing machines, okay, we can say input length in circuits also, but in circuits, since inputs are these discrete bits that you feed into the circuit, we also call it the number of inputs, or also called number of inputs. Okay.
yes.
So now that we have this, so here are some nice observations. Okay. So you have Turing machine M. So Cook-Levin was used to show that okay, you can convert the uh, Turing machine into actually a formula, and checking whether the Turing machine accepts it or not is as good as checking whether the Turing machine says yes or not. Okay, and checking whether the Turing machine has a satisfying assignment is as good as checking whether Turing machine has an accepting path or not. That's how it was going to show that, and SAT is contained in, because SAT is the exact problem of checking whether the circuit is satisfiable or not. Okay. Now here using Cook 11 we get a circuit. Now that's why I'll put a subscript here with length of x written here. Okay. So Cook 11, okay, gives me a circuit here. Now what was the ultimate aim of that? Well, this Turing machine checking if, or I'll call this circuit phi, okay, to be more accurate. Checking if Turing machine M is satisfiable is equivalent to checking, sorry, not Turing machine M is satisfiable, has a accepting path. Accepting path is same as checking if phi x is satisfiable. It's the same thing. And this is nothing but this characterizes NP, and this characterizes SAT. So any NP problem can be reduced to SAT. Any L in NP reduces to SAT. And that's how you showed that SAT is NP complete. That was the general idea of showing it.
Yes, but then the model in the left-hand side, Turing machine, so to show something as NP, we take the help of the non-deterministic Turing machine that it is, so it is, but here in the right-hand side, the circuitry must have been deterministic. So how is that possible that a non-deterministic model is being simulated or is being said equivalent to the deterministic one?
Right. Yeah. Because, see, for example, SAT has several satisfying assignments. No, it is able to characterize that non-determinism also pretty well. Because, see, at the same time, what is satisfiability doing? It is actually showing that how many certificates are there that satisfy this. How many inputs are there that satisfy this?
Yes.
Right. And so the question that we are asking is actually how many certificates will actually, so this is still kind of deterministic only. This circuit model is still deterministic only. You don't sort of make guesses out here, but because we are actually asking the number of satisfying assignments for this circuit. Okay.
Yes.
Okay.
But then still I could not understand that how the circuitry is simulating non-determinism.
The circuit is not simulating non-determinism. Remember, we are just taking a deterministic machine and translating it into another deterministic circuit.
So like say if a language is the element of NP, then what does it mean that this language is decidable by a non-deterministic Turing machine in the polynomial time? So this is one thing. And so if we draw an equivalence, I mean, if we draw a circuitry corresponding to the behavior of the NTM, non-deterministic Turing machine, then how is that possible? A circuitry which is completely deterministic and is taking a definite number of the inputs, is having a definite structure. Like
Yeah. But because see, this circuit, okay, is not telling you whether this particular whether the non-deterministic Turing machine accepts or not. Remember that. So you have this NDTM, okay, and it is a machine M. Okay, and here you have the circuit which are equivalent. We are seeing, right? This is, in fact, first of all, this is not happening. So a circuit will actually say talk about yeah. So the circuit will actually talk about the deterministic machine that is inside the non-deterministic machines. Different computational paths. So each of these are deterministic, and therefore this is what we are actually. The circuit actually talks about this. Okay. So what we mean is, if there is an accepting path, then if and only if there is a certificate here, that is, there is an input to the circuit that will actually satisfy this circuit. In fact, it's not even a circuit, it's a formula there.
Yes, so yeah, I do agree with this because when NTM is working, so NTM works in two phases. Say, in the first phase, we we predict the solution, and
Right.
then the deterministic Turing machine functions deterministically. Rest
Exactly.
of the option of the NTM is deterministic. So
Exactly.
here through the circuitry, we are realizing that deterministic part of the NTM, as you said.
Exactly. So because see, the reduction needs to be deterministic polynomial type, no? Because what was internally happening was a reduction.
Right. So then how can we say that something which is NP? So because in the beginning you said that if L is the element of NP and here it is simulating the satisfiability. So because
Yeah.
in the previous slide you said, so how can that be true? Here you said that L is the element of NP and checking if phi is satisfiable is satisfiability.
Right,
So
right.
yeah, what does it mean that L is the element of NP is same as? So basically, I mean, this circuit is taking care of only the verification phase and nothing else.
Right.
That's it. That's it. So once, I mean, we should know the solution in advance, and then the circuit can verify whether whether the formula is getting satisfied or not.
Yeah. For example, here
So
Suraj Kumar has said we can convert NDTM to TTM, and we can do the reduction to circuit like this. We can end non-determinism.
yes, so we can convert every NTM into the GTM.
But there will be a loss of time there. I
Yes,
mean,
yes.
you'll be Suraj, you'll be ending up with an exponential timed
Yes.
Turing machine, and then
Yes.
coming up with a circuit for that will probably take exponential size. But yeah, that is the next point I'm coming to, which is the size of the circuit.
But I agree with this. If we do
Okay.
take the verification part, verification definition of the NP thing,
Hmm.
if we know the solution, if we know if we know the certificate, that can be verified in the polynomial time in the left hand side, and that can be verified with the circuitry having the fixed number of the gates.
Exactly. So in fact, okay. In fact, what the if you look at take a look at the Cook-Levin reduction once again, it is actually talking about the verifier machine, which runs in polynomial time.
Yes, yes,
Yeah.
yes.
Okay. So yeah. So because again, yeah, the now the verifier machine is deterministic and so on. So, but what we end up is actually so what is the size of this circuit due to Cook-Levin? Is it exponentially sized? That can't be true, right? Because we are talking about reduction to SAT, and in polynomial time it reduces to SAT, and SAT, the circuit it takes as input should be polynomial sized. Oh, what's wrong with the pen? Okay, yeah. So resulting circuit due to Cook-Levin is poly-sized. Okay, this is clear, right?
Yes.
Yeah. So you can check it once. The resulting circuit is always polynomial sized. Now, one thing is obviously you are checking satisfiability on the circuit. Okay, that is when you took the took the non-deterministic Turing machine, or the verifier machine, and then try to make a circuit out of it and so on, get a polynomial size machine, a polynomial size circuit, and then check satisfiability on it. Let's not do that. Okay, let's do something more simpler. Let's do Cook-Levin only on a machine which runs in P, or machine for L in P. Okay, let's do Cook-Levin for a machine for L in P. Okay, and we use the same construction. We use the same construction, and then we get a circuit.
So I couldn't understand this thing. The machine for L in P, what did it mean?
No, the original was for a verifier machine, which was running in polynomial time. Here also we do the same construction. Okay, but remember, okay, what I'm trying to say is it was about checking satisfiability there in that particular problem.
Yes, yes.
Here it is no more about checking satisfiability. It is about checking whether given an input it will get satisfied or not. So what is NP essentially? What is NP essentially is you have a problem, you have a phi, okay, or you have a problem P, and there are several certificates for it, possible certificates for it, and then for some yk, and some of them are good for you. Is there any input that is good for you? Is that it's what it is asking, right?
Yes, so if we have a yes instance, then there exists at least one certificate, and I mean, wherein the verifier will generate one as the output. And if it is a no instance, then whichever certificate I give, every time I would be getting, the verifier would be generating zero instance.
Exactly.
Yes.
But now take the same verifier algorithm. For example, verifier, what do you have? It has an X and a certificate, right? Ditch this certificate. Just take X, or take the certificate as empty. Okay. Then what is that? It is nothing but a P machine.
Yes.
So
Right.
now the problem is, okay, whether X is accepted. In other words, or you can even say this single certificate that exists, is it a valid certificate or not? So that is another way to see it. Or you can say it is X a solution to a problem. Okay. How do you do that? In the equivalent Cook-Levin case, it is by evaluating the circuit.
Right.
Okay, so on X, evaluating on X whether it gives a 1 or not.
Yes. But then if we view it from the circuitry viewpoint, then we would be requiring polynomial number of the circuitry to simulate this, because for every input, for every phi, we would be requiring a separate circuit, and there would be the polynomial number of the phis possible, because the language is there in.
Yeah. And you mean the size of phi? No, you mean number of phi. Oh yeah, that could be infinite, because there could be infinite length.
No, not infinite here, because I think because L is in polynomial, so there would be polynomial number of the assignments possible. Polynomial
No,
number of,
but see, if a language L being in P does not mean that there are only polynomially many candidates in L.
so the length of the,
Yeah.
because even if there would be infinite number of the lengths possible, infinite number of the strings possible, but then every string would be of the finite length.
Yeah.
Yes, so there would be infinitely many, yes, right.
Exactly. Right. So what do you actually? Actually, I didn't want to go too much in depth. Okay, but you get the gist of it, I think. Why did I? How do I can't decrease the size? Okay, because like the L and L in NP, this is a language in P. Now, what is this language? This is circuit value problem. Okay, and by the same argument, so by the same Cook-Levin reduction, you can see circuit value problem is P complete.
Okay. Okay.
Okay,
Yeah. And how much effort is required for this reduction? Say reduction to five. I mean,
how much what?
how much effort is required
Oh
for
yeah,
this
yeah,
reduction?
it takes polynomial time.
But then if reduction is taking polynomial time, then again
In
you
fact, I think it's log space from what I recall. Yeah, what were you saying?
so if it is log space, then it is fine, but not the polynomial time because if you are reducing
Ah,
something to
right,
the
right, yeah, yeah, yeah. That's why it makes sense. It needs to be log space, and it is log space.
yes.
It is a log space reduction that does this.
Yeah, I have a question out of curiosity, and it has nothing to do with this.
Huh,
But so, do we have a complexity class having v of x comma x? Like here you have written v of x comma epsilon is a p class,
huh.
right? Wherein we do not require any certificate, and the verifier itself can solve the problem in the polynomial time.
Right, right.
My question is that do we have such complexity classes wherein for a verifier the certificate is the column itself. So column itself, I mean, acts as a certificate, and the verifier can verify. I mean,
Yeah, yeah. But for the circuit, it will be interpreted as an input only. For
no,
the
I'm not asking.
certificate, yeah, you can take this entire thing as an input only, which can be partitioned into two parts: the certificate and the input, actual input. But that brings me an interesting idea that um, okay, can you think of randomization in circuits?
Uh, So randomization in circuit would mean that okay, so for the in for the circuitry, I keep some space for the input,
Huh,
and I mean I keep some values for the inputs, actual input, and some values for the random bits.
exactly. So that is how randomized circuits work. So these are random bits, okay, and these are um, in actual input, and this is circuit C. And if the random bits are good, actually they are taken with from a uniform distribution, then the probability that C outputs 1, okay, if L is in the if L X is in L, if X is in L, then the probability that C outputs 1 on X over the random bits over a good distribution on polynomial or not polynomial on some key random bits should be greater than equal to 1 by 3 or 2 by 3 or whatever. So this is one way to characterize randomized circuits. Okay.
Yeah, my question was slightly different. That wherein the problem itself. So say for the verifier, the first x is the what? First x is the problem. First
Hmm.
x is the system. And the second argument, which was y, is a
Hmm.
certificate.
Hmm.
So we have a complexity class wherein the v x comma x, I mean wherein the problem itself x as a certificate.
Oh, okay. I thought you meant it in the circuit scenario. Okay, so v comma x, x is its own certificate.
Yes, X itself acts as a certificate. I mean, do we have some? I mean, I was just viewing it from that. I mean, from that recursion theorem kind of the thing, wherein we run the Turing machine, and the output of the Turing machine is the description of the Turing machine itself. Like
Okay,
the
yeah.
like the program's coins, wherein if I run the program, then the output of the program is the program itself. I hope
Hmm.
that.
Um, well, I do not know. I mean, certainly you can define such a thing, but see, okay, so what is the what is the problem that we are defining here? That is, given a machine, is it true that for that particular input, there should be some kind of quantifier for this? Otherwise, it won't work. Uh, what are you asking exactly? Given a problem and an input, is it true that the input itself is a verification for it for that input?
Yes. Like say we can think of something similar to the
But
self-healing
then,
program
yeah,
or
but then,
verifiable.
yeah. Unless the verification takes more than polynomial time, it's not interesting
Uh, So,
because
so, so since the length of the x is polynomial here, even
exactly,
if it's a certificate of y, that is also a polynomial function of the length of the x only.
yeah, exactly. So, yeah, unless the verification takes more than polynomial time, then otherwise this problem will be trivial. But still interesting. I do not know any such classes or such exactly this particular problem being studied. Okay,
Yes. So,
okay,
uh, thanks.
okay, sure, no problem. Okay, randomization in circuits, sir. Can you explain once in short? Sure. So randomization in circuits is the following, Suraj. It's that, so you have an algorithm, right? So this algorithm works as follows. It makes a computation. It begins its computation, and then you can imagine it to do some deterministically going to some point, and then it suddenly tosses a coin, and then it lands on heads or tails, and then it starts tossing its coins on different places, or deterministically goes some places and then starts tossing coins 0 1 and so on. This is one way to view the algorithm, a randomized algorithm. Let's say it is a BPP or an RP algorithm. Another way to view the same algorithm is that instead, okay, instead of tossing coins on the way, it tosses all the coins in the beginning only. Toss, toss, uh, toss k coins. Okay, 0 1 1 0 1 1, and these are purely random. These are purely random coins. And then what does it do? It simply traverses that particular sequence. First a 0, okay. So this is the computation. It simply traverses, it pretends like the first toss was a 0, and then the next toss was a 1, then the next toss was a 1, and so on. And so it does not need to explore these. It does not need to explore these paths only. Getting it? But it's not a very novel algorithm. There's nothing new here. Instead of tossing coins on the way, it's just tossing it at the beginning. So it can be seen as feeding the random bits externally. Feed random bits externally. Well, what is a randomized algorithm? Well, if you give it purely random bits, then it has a good chance of succeeding, right? And then if I'm feeding the random bits externally, okay, and I'm giving a promise that I'll give you really good random bits, okay, they are purely random bits, then there is a good chance of succeeding. There's a good chance of succeeding, right? Yeah, that's how I view how randomized circuits can also be viewed. You have a circuit and you have an input side, the real input, and this part are random bits. Now again, the guarantee is that I'm going to guarantee you that I'm going to give you really good quality, high quality random bits. They appear very random. Then the probability that the circuit will be succeeding is also very high. That is, if X is in the language, then probability over the random bits, okay, uniformly sampled from. This means the random bits are really good, okay, that the circuit says yes whenever X is in the language is very high, is some greater than epsilon. Okay, so this is what a randomized circuit looks like. Okay, Suraj, is that clear?
Yes,
Okay. 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 Coil also. Okay. So, okay. Now let me come back to my point here. That is that, okay, I know that Cook Levin, okay, by Cook Levin, L is in P is as good as checking whether a circuit phi is phi L is in P, okay, and X is in L for an L in P is as good as checking whether phi is phi of on that input X is equal to 1 or not. And furthermore, phi is size of phi is polynomial via Cook-Levin. Now I know that firstly for NP characterization was whether it is satisfiable or not, and here it is whether it evaluates to 1. The input is already given to you, whether on that input it is equal to 1 or not, or in other words the CVP problem, circuit value problem, which is P complete. So any Turing machine can be converted to a circuit. Okay, now this is an important connection here. Okay, any Turing machine of which runs in polynomial time can be converted to a polynomial size circuit. Is it true that if I now okay, any polynomial, okay, or I'll write P time Turing machine can be converted to a poly-sized circuit family. Let me call it C. Okay, can be converted to a polynomial size circuit family. Is the converse true? That is, if I have a circuit that is of polynomial size given polynomial sized circuit C on n bits, okay, and it can be characterized by a Turing machine taking polynomial time. Is this true?
So what is the size of a circuit?
Polynomial size circuit.
So what comprises of the size of a circuit? I mean, what is there in the size of the circuit?
Oh, okay, the size is the number of gates, number of and or not gates.
Okay, okay.
Okay. So what do I mean by characterized? It means when the what is meant by characterized? It means when Cn says x is equal to 1, then Turing machine says accept, and Cn says x is equal to 0, then Turing machine says reject.
Oh, so once the circuit is ready, then we can simulate any number of the strings into it. I mean, exponential number. I mean, we keep on experimenting. We keep on giving the strings as the input, and the circuitry will be generating the 1 and the 0 as the this thing.
I mean,
So
we are not verifying whether circuit is satisfiable by the way. Okay. We are checking
this
the evaluation. Given your input to the circuit is also given, it's fixed.
okay. Okay, so if input is also fixed, then it is can be characterized by uh, okay, okay, uh, okay. So since the size of the circuitry is fixed and it's polynomial, it shows that whenever I give x as an input and I'm
Hmm.
getting the solution,
Hmm.
something whose size is polynomial.
Hmm.
So something whose size is polynomial, need not necessarily implies that time is also polynomial. We have seen this during the space complexity as well. If the size is polynomial, then Turing machine may take exponential amount of time to get executed.
Okay. See? Okay. So, but actually, it's possible. Actually, it's the evaluating a circuit is not very difficult. evaluating a circuit using a Turing machine. Okay, let's say you have a circuit which looks like this, OR gate, AND gate, and so on, or and and it may be something like this. Since it's a circuit, it may be feeding like this and so on. Okay,
Yes, but then circuit used to be a DAC,
circuit used to be a DAG. That's correct. No problem.
but this is not a DAC
How is this not a DAG?
because all the arrows by default are pointing upwards.
Right.
So
So
this
it
is
does not have a
called.
cycle.
Oh yes, yes, yes.
Okay. So let's say this is G1, G2, G3, and so on, and G4, G5. So what you do is simply make some variables, declare variables. Okay. Let's say V1, V2, and so on till V some V K if there are K gates. And then what you do is you look at them level by level. You can do like a BFS to go by level on the opposite side, and go start from the inputs, and then start evaluating each gate here. Some J plus one, and so on, and start evaluating them. Evaluate gates GI bottom up and store output in VI, and you keep doing this. Go bottom up and start evaluating each of them, and then if output gate, which is G1 for us, is equal to 1, then accept, else reject. And how much time does it take? Time is equal to number of gates roughly.
Yes.
Which is polynomial.
No, I was about to say this, but then somehow I'm mixing this idea of circuitry with the space thing.
Yeah. Space,
So
we are allowed to take point. Remember, we are. I know you are thinking of P space. That's why you are feeling this
yes,
way.
yes,
Because P space, it's not clear whether it runs in polynomial time. But the key idea here is that any P Turing machine, any P algorithm is allowed to take polynomial space as long as it runs in polynomial time. That is what
that's
is happening here.
yes, that's true. But then, if I'm having a circuitry of the polynomial size, then why can't view this circuitry of the polynomial size as uh, something as a complexity class wherein the space is fixed? Because I mean, circuit can be reused similar to the space.
Oh, okay. That is a wild variant. I've never thought of that. Circuit can be reused.
Yes, circuit can obviously be reused every time. I mean, whenever a circuit is ready, it is ready forever, and I can
Okay. Yeah. Right. Yeah.
I can reuse it. So why don't we view, I mean, the some computation in the circuitry similar to something wherein we have been given a space and which can always be reused,
Space which cannot be reused.
which can always be reused. So why don't,
Space
yeah,
can be
why,
reused. So we can do that here also. Once, let's say, we are sure that a gate is not going to appear later on, we can reuse that space.
yes, so then,
That is actually the heart of space complexity also, right? For example, that is what happens in say showing that reachability is in NL. You just keep one pointer and then keep reusing that.
yes. So something similar. So this I view the circuitry as a combination of two things. Number one, it has got something which is similar to the Turing machine. I mean, the computation or the calculation or the processing similar to the Turing machine, number one. And second thing is, since its structure is deterministic, it has got the finite, I mean, polynomial amount of the space, and that space can be reused. So,
Right.
I mean, so can we mix these two things? I mean, to explain the calculations related to the, I mean, using the circuitry.
Um, Well, yeah, definitely. I'll come to that.
Okay, okay,
It's good thinking. For example, so I think this kind of question answers your question maybe. So it's kind of like what does time in Turing machines correspond to in circuits? What does space in Turing machines correspond to in circuits?
yes, yes.
Something
So
like
the
that, right?
yes, yes, very true, very true. So the time corresponds to the, I mean, probably could be related to that how high we go in the circuitry,
Right. Good.
and the space probably would corresponds to the number of the, I mean, these gates, etc., or the input pins available in the circuitry.
Well, see, there is a concept of a layered circuit. Okay, you can think of the circuit in terms of layers.
Oh, I see, I see.
So I
Okay,
can always, push and pull this circuit to be nicely layered. Okay.
yes,
For example, if I keep a sort of a dummy gate here. Oh, okay. Something happened. Okay. Yeah. For example, I keep like a dummy gate here, which is something like an and with a one here. Okay. Then I've
yes,
made the circuit layered, adding dummy gates. Right.
yes,
So I've made the circuit layered that way. So now I've thought of it as layers. So now the idea is that since the circuit is layered, okay, think of the width of the circuit as the largest layer in the circuit. The
yes,
the number of
yes,
gates in the largest layer of the circuit.
yes, yes,
Since it is layered, the bottom gates will never appear again. So I can reuse that space. So what
yes.
does space correspond to in a layered circuit?
So space would corresponds to then the things which can be reused, but still I believe that okay, so the last layer, the number of the inputs.
Well, your circuit may look like it may look from small to big and then again small and something like that.
Oh, I see.
The width may increase and decrease, but won't the space be corresponding to the largest width, which is exactly the width of the circuit?
Yes, and what this width of the circuit
Width
comprises
of the
of?
circuit is the maximum width of any layer.
Yes, so that can also be considered as a space. I'm not sure.
Exactly. So that can be considered as an analog to space.
Okay, okay,
Okay. So you can actually translate into measures. So later you see a few more models of computation, and it will actually fit in better than this. Some of the measures, okay, like space. There's a better model to actually capture space. Okay. But I'll not reveal it right now. Okay.
okay,
Okay. So, but what is the takeaway from this? That the number of gates is polynomial. So we have two things now. Okay. Two things. One is poly-sized circuits. Okay. Poly-sized circuits can be converted into um, polynomial time Turing machines, and also that polynomial time Turing machines can be simulated by polynomial size circuit families. Okay, I should be writing circuit families by doing the Cook level. Isn't it true? So they are almost one on the same thing. Okay. So what is P size, which is also called P slash poly, is the class of uh, languages decidable by polynomial size circuit families. Okay. P size is equal to P slash poly, which is the class of languages which is decidable by polynomial size circuit families. And what is P? P is class of languages decidable by polynomial time Turing machines. Right. So, and we are saying these two are Almost the same thing. So can we say that P is equal to P slash poly? Can we say this? Okay. First direction. Can I say P is contained in P slash poly?
That
That is,
seems to
can
make
any
sense.
polynomial time Turing machine, any language that a polynomial time Turing machine decides, can it also be decided by polynomial size circuit families?
Yes, yes, definitely.
Yes. We just saw it how. Yes, by Cook level.
Yes.
The fact that such a circuit exists is itself enough. Circuit family exists is itself enough. Now let's try the other way. Is P slash poly contained in P?
So yeah,
Now the question is a bit different. Okay, the question is, we know that a language is decidable by a polynomial sized circuit family. Can that language be decided by a polynomial time Turing machine? Well, we saw that evaluation is enough. We
so
can
we also
evaluate a circuit.
yeah
So it
we also
looks like we can do it, right? Yeah.
yeah, so we also saw that NTM can be simulated by this circuitry of the polynomial size. Just now
Right.
we saw, right?
Right.
So because we saw that L is the element of NP and
Hmm.
then a satisfiability. So
Right.
certainly this P by poly is more powerful than this P. P by poly can do lot many other things also which are not
Yeah,
there.
yeah. But what is but here, okay, you said it's more powerful, right? But why exactly? Okay, well, that is one argument. But can you see something wrong with this? Okay, so let me so give an idea. Okay, here is an idea. Tell me what is wrong. Okay, L is a language in P slash poly. Okay, via circuit family CN. Okay, now here I'll give a P machine. Okay, now claim is here is a P machine for L on input X. Okay, now let's say on input X, what it does is evaluate step one, which we evaluation we already saw it's possible in polynomial time. Evaluate Cn on X. If Cn on X is equal to 1, then accept, else reject. This takes polynomial time, no? And this would be showing that P slash poly is contained in P. What is wrong here?
Uh, so the yeah. So the thing is that we are evaluating. So this, I mean, this claim only says that P is contained in P by poly, and this does not say that P by poly is contained in P.
No, no, because we are taking a line. So to show that P slash poly is contained in P, what should we do? We should say
So
that a language in P slash poly can be simulated by a Turing machine, which runs in polynomial time, right?
yes,
So
yes,
the direction is correct,
yes. But then in the step number one, we are evaluating the Cn on the given string x, and if
right?
this is
Which
equal
takes
to
polynomial time on n.
yeah, and yeah, yeah, and else it is getting rejected. Yes. Uh, okay. Okay.
So
So
okay, should I tell? Yeah,
yeah. So but then yeah. So P by poly would be having many such circuitries C by X,
right.
right? So will that create a problem here? I don't know.
Exactly, exactly. The good. Cn is an infinite family.
Yes. Yes.
How did you suddenly come up with C of x?
Yes, yes, right.
How did you suddenly come up with C of x? Right? How did you do that? It's not possible. I mean, always, right? Maybe. unless unless I advise you on what may be the correct circuit to
Right.
evaluate. Unless I do that, or unless you are, it is true that for that particular circuit family, you can compute that circuit family for that particular input in polynomial time.
Yes.
Right.
Yes.
So there are two possible cases. One case is the magical advice case. Another case, which is the most simplistic case, is when the Cn, the description of Cn circuit family is computable in polynomial time. Okay. So one case is when this magical being will advise you. In this case, what will happen? In this case, an advice is given, and advice is defined as a function which takes in an input length. It takes in a natural number. Advice h takes in a natural number and gives you some string, which is polynomial. And for our case, advice h takes in the length of the circuit n and gives us what? It gives us C of n. If such an advice is given to us, then we can do that. Then again we do this part. And if it is computable in polynomial time, if it is true that it is computable in polynomial time, then what will we do? Step 1 will change now. Compute Cn for length n, and these two steps will follow.
I could not understand case two. So why case two exists?
Case 2 exists. Yeah, case 2 is it may be true that I can give you the circuit. It is possible to compute the circuit family in polynomial time, right? For example, like I said, the circuit that I can tell I can polynomial time design a circuit which verifies if there is at least one or
Right.
1 0, right? You give me the answer, one AND gate with uh, wires to all inputs.
Okay.
Right.
Okay.
That can be done in polynomial time. And give me any length, I'll do it for you. The Turing
Yes.
machine can himself do it. He can himself come up with a circuit.
Yes.
So that is exactly what the Turing machine will do. It will compute the Cn for that particular length and then evaluate on that x and then accept, otherwise reject.
Yes.
And here in the magical advice case, it may not be true that in polynomial time it can construct the circuit family. So the magical advice will actually give you, for that particular length, then it will give you all the circuits. Sorry, it will
Yes.
give you that single circuit.
Yes. similar to non-determinism kind.
Similar to.
Non-determinism kind of a thing. Then all of a sudden, I mean, through some magical advice.
Yeah, yeah. This is even stronger than non-determinism. Yeah, but it is similar to that.
Okay.
Correct. So now what we have is the following. Um, now what we have is we have something called P uniform circuits, which is circuits whose description can be computed in polynomial time. Okay,
Yes.
and now this case 2 actually captures simulating via P algorithm, right?
Yes.
So P uniform P slash poly is equal to P. Getting it? So it's actually small p. P uniform P slash poly is equal to P. It's not true that P slash poly is equal to P. But P uniform P slash poly is equal to P.
Yes. So can you explain this P uniform circuitry again? That I mean, what does it mean that having computing the description of the circuitry in the polynomial time? Who is going to compute? I
The
mean,
Turing machine.
oh, I see.
Okay, I'll explicitly write it. Turing machine computes Cn for length n. Okay. So yeah, this is the uniform circuit. So later on, this point will come up, left and right uniformity. Okay. So it means, don't be afraid. It just means if I say something like log space uniform circuits. Okay, if I say something like log space uniform circuit, it means the circuit description for that particular length can be computed by a Turing machine which takes only log space.
Oh, I see. And yeah, just out. I mean, my question is that how Turing machine generates the description of a circuitry. I mean, it's like that the Turing machine itself is generating some kind of the program. A program is generating some kind of the program kind of a thing.
Yeah, in a way you can imagine that. You can just think that, okay, for example, let's say Turing machine needs to generate a circuit for the same problem, whether the input has at least one or not.
Mhm.
Then it needs to come up with this, right?
Yes.
So what is this? This is just a graph,
Yes.
and so it can make an adjacency matrix where there is an output node. There is an output gate and all the inputs, and these are all the inputs. Okay, these are all the inputs will be connected to that.
That's true. That's true. But the Turing machine can verify the things. But how can Turing machine generate a thing? I mean, generate
Oh, of course,
something.
I can make the Turing machine do that. No, I can write it in the description. No, for example, for an input n, okay, I can say for I in 1 to n, make an adjacency graph as follows. Okay, first of all, set A is equal to all zeros matrix n cross n. It is an all zeros matrix, and then I can say, okay, for I equals 1 to n. Okay, what you can do is for that output, so output will be n plus 1. So the matrix is n plus 1 because there are n nodes plus 1 output node. Okay, the n plus 1 cross n plus 1 matrix, where I can say A at that n plus 1th row, which is Okay, n plus 1th row is equal to comma ith column, which means uh, is equal to. And what will it do? It will build an adjacency matrix where I have these are 1, 2, 3, 4, and so on till n, and this is n plus 1. And then this is 1, 2, 3, 4, and so on. And there is n, then there is n plus 1, and this is the gate that is the output. And here I can write, you know, 0, 1, 1, 1, 1, or actually the opposite 1, 1, 1, 1, and at the end 0. 1, 2, 3, 4. Well, I've just built an adjacency matrix, or rest are all as zeros. That exactly captures this graph. Right. And to show OR gate, maybe I'll use a 2. And maybe to show negation gate, I'll use a 3 or something like that. Anyway, it can do that.
Yes. Yeah.
Okay.
Yeah. I will think more on this because yeah, it is quite strange for me to to understand this thing that how a Turing machine is generating a program for
Sure.
this.
Sure, sure, sure. But there's a reason that I went through all this process. Okay. I wanted you to see one important thing.
Yes, yes, that I get.
So that is the following. Okay. Oh, said your mic is on. So there is a lot of feedback. Hello? Oh, yeah, yeah. I said you were saying something. Oh, I'm not able to hear you properly. Your voice is sounding very muffled. No, it's still very. Yeah, okay. I can hear you now. Yeah, Suraj. Yeah, I think Mike. Okay. Yeah.
It is 7. So it is 7:40. So in case if you don't want to, deliver anything else, then yeah, we can stop here.
Oh, yeah, yeah. Sure, sure, sure. Yeah. So what I want to go is Seth, can you turn the mic on mute? Okay, I think the feedback is from my. Okay, that's what is feeding. Seth, can you turn your mic on mute? Okay. Put up. Yeah. Okay. So let me come back to um, yeah, right. So oh, okay, I can mute it from my side. Okay, great. So yeah. So okay. So the final points, right? So P versus NP problem. P versus NP problem. Can we tackle it using circuits? Can you prove that P is not equal to NP via circuits? Okay. So or can you prove that P is equal to NP via circuit? Here is a way. Prove that SAT needs SAT is computable by polynomial size circuits. Okay. Prove that SAT is computable by polynomial size circuits. Okay, and not just polynomial size circuit, so uniform polynomial size circuit. So P uniform. Sometimes this is not written, but if it is computable by polynomial size circuit, it is in P, so SAT will fall down to P. But it is most believe that P is not equal to NP, right? So how do you separate P is not equal to NP? Next idea is prove that there is a language L which is in NP that needs at least, say, n to the, okay, I'll write super polynomial. Okay, super polynomial, I think I already told you. Or exponential is also enough. Prove that in NP there is a language which will at least take more than polynomial size, or a harder thing to prove actually would be takes exponential size to solve it. Okay, if you show that, then it is enough to separate P and NP, because if it were in P, then it could always be solved by polynomial size circuits, right? So if it it requires at least exponential size circuits or even super polynomial size circuits, then you are done. You separated P and NP. Yeah, Goel, you wanted to say something?
No. Yeah, my mic is accidentally on. Yeah,
Yeah.
nothing.
Oh,
No,
okay.
that's
Okay. So that's one way to separate P and NP, and these are what are called lower bounds, circuit lower bounds, and this is a huge area of study. Okay, and then people tried attacking circuits using lower bound, attacking P versus NP using lower bounds left and right, and unfortunately, okay, what we need is super polynomial size lower bound. No. Best known lower bound is some 5n. We just know linear lower bound. That too, I think little low of 5n or something like that. So this is the state of affairs. So what we are looking for is super polynomial size circuits, but unfortunately, the best known lower bound is just 5n. And proving lower bounds is in notoriously difficult task. Okay, even to prove something like a lower bound for parity, okay, XOR, that is, even to show that XOR requires certain size circuits, very small size circuits, even for small size circuits, it is incredibly difficult job. It turns out, and to prove that a particular circuit requires exponential size circuits or super polynomial size circuits, that is insanely difficult to do.
yes.
Okay. In fact, we don't know of an explicit problem that requires exponential size circuit. And in the lectures, you must have seen Shannon's theorem, which says most problems need exponential size circuits. Most problems, more than half of the problems, more than half of the language, 2 to the n by n, to be exact. So there's a size required. Okay, so yeah, most languages require exponential size circuits, but we, unfortunately, it's ironic, okay, and sad state of affairs that we are not even been able to come up with one language. It need not be in NP even. It may be in EXP or NEXP, whatever, that requires exponential size circuits. So yeah, so the best known lower bounds is 5. Is that clear?
Yes, yes.
Okay. Now, okay, it's already 7:48. Okay. Okay. So, is there any question from the previous assignment that you want me to quickly solve? So, okay. So this is my own question, but I didn't get time to do it. Maybe next time in the morning, in the beginning, I'll do it. Um, okay.
So what is the
Yeah.
topic of the next session? Which topics would you cover in the next session?
Yeah. Right. Okay. I think it's circuits continued, right? Wait. Let me see. This is week 7, week 8. Yeah, it's still circuits. Parity not in AC0. Um, Hadelman's theorem, PIT. Okay, isn't randomized NC. Okay. Okay. So it's still circuits only. It's about circuit load bounds only. So anyway, they are very specialized topics. So even if I use the same questions, it will still be fine.
Oh, okay.
Okay. So just let me know if you want me to solve any of these questions. Um, okay, this question has a slight problem, but okay, and this ninth question I tackled in the last week, so please check it out. Okay, last week, towards the very end, and okay, mostly they are simple questions only. You should be able to do it. So here is a question that I wanted to do today, but I don't think I'll be able to. It's a bit too much for I think 10 minutes. This question I'll do first thing in the morning. What I wanted to do was make sure that you understand the circuit model very well before we dive into solving questions with it. And but take a look at this question. I'll be solving this question next time. It's about monotone circuits, and yeah, please you can attempt it once. Okay,
Yes.
you can make an attempt once. And with that, we'll end the session. If you have any questions, then you can ask me. And Goel, I'll look into that. Yeah, please mail me also. Okay.
Yes.
And yeah, I'll look into that. Oh, what was that? Some.
Yeah, tipping point thing that
Yeah.
density of the Boolean.
Yeah. Satisfiability thing. I'll look into that. So if you have any more questions, then I'm here uh, for a few
Thank,
minutes. And if not, then we can call it a day.
yeah, thank you so very much. Despite, I mean, it seems that you are not well today, but
Okay,
it
thanks.
took whole 2 hours session, and it is, I mean, almost 8 now, and in 2 minutes, it would be the shortest session.
Yeah,
Thank
yeah. Thank you, Goel. Yeah, I'm not feeling too well today, but I hope that it didn't affect the flow of the class too much. Although I think I went a bit into too much into theory, I couldn't solve too many questions.
you. No, the today's session was so very fantastic, and I understood so many new ideas. I mean, in today's session. Thank you
Yeah.
so
Oh, okay. Thanks. Thank you. I'm glad.
much. Bye bye.
Okay. Okay. Yeah, sure, Suraj. Okay then. See you next time. Okay. So, Seth, if you have any questions, just let me know. Okay. I think not. I'll just stop the recording.